Hello, everyone. I am Colin Kurz, and this is my report for Lab 5. The purpose of this lab was to analyze the falling motion of a magnet through a cylindrical tube of aluminum foil and compare it with a glow script model of the motion, which was created using physical principles such as Faraday's law. The result was that the model is fairly accurate to the results of the physical lab, with the magnet spending 1.053 seconds in the tube in the model versus roughly 1.17 seconds in the real experiment. The fundamental physics principles of this lab were the magnetic field of a dipole moment mu, which was used to find the strength of the magnetic field from the magnet at the tube, the magnetic flux, which was used to help find induced current in the aluminum foil using Faraday's law, the Biot-Savart law, which calculated the force exerted on the aluminum foil with the current, which was then used to find the force exerted on the magnet using Newton's third law, and Newton's second law, which was used to iterate net force and distance fallen in the tube. In this lab, the system was the magnet, tube of aluminum foil, and the earth. The surroundings were everything else. The experiment consisted of recording a magnet being dropped through the vertically held tube 6 times. The north end of the magnet was facing upwards at the start of each drop. The timestamps in the video where the magnet entered and exited the tube were used to find the time that the magnet spent inside the tube. This presents two potential errors. The first being that the tube wasn't held perfectly vertical, and the second being that the timestamps were limited by the length of one frame. Next, code was written to simulate the motion of the magnet through the tube. This code assumed the tube of aluminum foil to be a collection of tiny, imaginary conductive rings stacked on top of each other. This will be important later. As per usual, the first thing to do is to set up some constants, notably, in this case, the resistivity of aluminum foil. Then, using the dimensions of the tube of aluminum foil and a provided function, the digital tube of aluminum foil was created. Finally, the magnet was created using the mass and mu mag recorded in Lab 3. This stage of the code is where some of the important functions were set up. First, the general equation for the magnetic field from a magnetic dipole was used to find the strength of the magnet's field in the tube. Using this, the function for time derivative of flux was created in a rather unconventional way, where the numerator and denominator of d flux dt were calculated separately and then put together. This result was very important as it was equal to the electromagnetic force in the foil. It is a direct application of Faraday's law. Finally, a large simulation loop was run so that all of the forces and fields would change appropriately over time as the magnet fell through the tube. The dflux dt function was called and used to find the current in the imaginary rings in the tube. Then the B field function was called to find the B field at each ring. The result of this, along with the calculation of the current, was used to find the magnetic force on the rings, which was used to find the magnetic force on the magnet using Newton's third law. This was then combined with gravitational force to find the net force on the magnet, and from there, Newton's second law was used to find the velocity and displacement of the magnet. The resulting graph of velocity versus time shows that the magnet stopped accelerating while in the tube, and then continued to accelerate downwards due to gravity upon leaving. This matches with the conclusion reached by the experiment, where the magnet spent much longer in the tube than it would have if it was dropped through the air due to induced current and the resulting magnetic force created by the tube. This amount of time spent in the tube in the model was also similar to the amount spent in the real experiment. It was about 0.1 second off. Some final questions remain. What if the resistivity of the conductor were reduced to as close as possible to zero? How would the dynamics of the falling magnet change? Well, because current and resistance are inversely related, a much reduced resistivity would lead to a much increased current. This larger current would lead to a larger magnetic force, causing the magnet to fall much more slowly than it did in this experiment. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? This answer depends a lot on where and how the holes are cut. If the flow of current is stopped in some places by the holes, the magnet could fall faster. It could also tumble around inside the tube more and experience more or less acceleration, depending on where the holes are.